Hello all. In my last class, I discussed PN junction in open circuited condition or unbiasing condition. And also, I discussed calculation of the built-in potential in case of open circuited condition. Now in this class, I will start with the calculation of electric field. Calculation of maximum electric field at the junction. Next, put the heading calculation of maximum electric field at the junction. Right. Here, to calculate the maximum electric field, actually here consider a PN junction for which the charge density within a depletion region is given by. Consider a PN junction for which the charge density within a depletion region is given by rho v equal to minus Na into E in the region X value lies between minus Wp and 0, right? Next, rho v equal to Nd into E if X value lies between 0 and Wn. Otherwise, rho v equal to 0. Otherwise, rho v equal to 0, right? Yeah. First, consider region X value lies between minus Wp and 0. Region lies between minus Wp and 0, right? See how to calculate the electric field actually by using Poisson's equation actually. By using Poisson's equation. What is Poisson's equation actually? I already told. That is d square v by dx square is equal to minus rho v by epsilon. But in the region of minus Wp and 0, what is the rho v actually? Minus Na into E, right? Then d square v by dx square is equal to minus of minus Na into E by epsilon, right? Which is equal to Na into E by epsilon. Now integrating on both sides. Integrate on both sides. Then the expression is dV by dx, which is equal to, this is Na into E into x by epsilon plus C1. After integration, this is the expression actually. Let us consider this one as equation 1, right? What is dV by dx actually? The dV by dx is nothing but simply it is what actually electric field, right? Here to calculate this C1 actually, to calculate C1 use electric field versus distance plot. In case of open circuited condition actually, what will be the electric field versus distance plot? This is right. This is minus Wp and this is Wn, right? This is the electric field versus distance plot, right? So use electric field versus distance plot. See from this, at x equal to minus Wp, what will be the electric field value? 0. Electric field equal to 0, right? If electric field equal to 0, then what will be the C1 values here? This will be 0 and this is what actually Na into E into minus Wp by epsilon plus C1. Now what will be the C1 here? C1 is nothing but Na into E into Wp by epsilon, right? Now this is equation 2. This is equation 2 actually, right? Now substitute equation 2 in equation 1. substitute equation 2 in equation 1. Then dV by dx is equal to Na into E into x by epsilon plus C1. C1 is nothing but Na into E into Wp by epsilon. Right? Now, this one, consider this one as equation 3. Right? But what is the dV by dx? Actually, dV by dx is nothing but electric field actually. Right? Here, in case of PN junction actually, where is the maximum electric field is present actually at the junction. At the junction means what is the value of x actually here? 0. Right? See, to calculate maximum electric field, consider the condition at x equal to 0. See here, in a PN junction, maximum electric field, maximum, write down like this, maximum electric field is present at the junction or at x equal to 0. At x equal to 0, right? Then Emax equal to Na into E into Wp by epsilon. This is the maximum electric field value. This is considered as equation 4. Okay. Similarly, in the region of 0 and Wn, what is the maximum electric field actually? The maximum electric field is nothing but Nd into E into Wn by epsilon. Right? Yeah. Consider this one as equation 5. Right? Yeah. Copy. This is the maximum electric field in case of open circuited PN junction. Copy. Right. Completed? Yeah. Next one, I will continue the derivation here. See, from equation 4 and 5, see, both are maximum electric field, right? So from equation 4 and 5, that means equate equation 4 and 5, because both will be same. If we equate both maximum electric fields, then we will get a relation between carrier concentration depletion width. Right? See here, equate equation 4 and 5, then Na into E into Wp by epsilon is equal to Nd into E into Wn by epsilon. Right? Then what is the final expression actually? Na into Wp is equal to Nd into Wn. See, from this equation, what is the conclusion actually? Right? In case of PN junction actually, the depletion width is inversely proportional to the carrier concentration. In case of PN junction actually, the depletion width is inversely proportional to the carrier concentration. See all of you. See here, for example, if acceptor concentration is greater than donor concentration, then Wn is greater than Wp. Right? Similarly, if donor concentration is greater than acceptor concentration, then Wp is greater than Wn. Okay? For example, if Na equal to Nd, means if the PN junction is doped equally, equal number of acceptors as well as equal number of donors, then what about the relation between depletion with Wn equal to Wp? Right. That means what is the conclusion actually? See here, if the PN junction is one-sided heavily doped PN junction, If the PN junction is one-sided heavily doped PN junction. One-sided heavily doped PN junction means like this. If it is P plus N or P N plus, right? Then the depletion width can occupy the lightly doped side. Means, for example, in case of this sample, P is heavily doped. That means the depletion width occupy N side. For example, in this sample, N is heavily doped. That means the depletion width can occupy P side, lightly doped side. Okay, if the PN junction is equally doped means P and N, then the depletion width will occupy both N side as well as P side equally. Here, W1 equal to WP. Very, very, very important point. Right on. Next, write on the notes. Equate equation 4 and equation 5. Equate equation 4 and equation 5. Right? Copy this. Copy the statements. And also copy this one also. Right, write down. Note. If the PN junction is one-sided heavily doped PN junction, if the PN junction is one-sided heavily doped PN junction, then the depletion width will occupy lightly doped side. The depletion width will occupy lightly doped side. Lightly doped side. Right. Next topic. Calculation of depletion width on N side and P side. Next heading. Calculation of depletion width on N side and P side. In bracket Wn comma Wp. Calculation of depletion width on N side and P side. Right. See how to calculate depletion width on N side and P side. First, I can define total depletion width. Total depletion width is nothing but what actually Wn plus Wp. Right. Consider this one as equation 1. Already we know Wn into Nd equal to Wp into Na. Right. From this, what is the Wn value? Actually, Wn is nothing but Wp by Wn into Na by Nd. Yeah, consider this one as some equation 2. Right? Substitute equation 2 in equation 1. Then W equal to Wp by W. Sorry, I think there is no W1 here. Here there is a wrong actually. Small correction. Here there is no Wn. Wp into Na by Nd plus Wp. Right? Yeah. From this actually, common the Wp here. Then Na by Nd plus 1. From this, what is the Wp here actually? Wp is nothing but W into Nd by Na plus Nd. Yeah, consider this one as equation 3. Right? Similarly, Similarly, Wn is nothing but W into Na by Na plus Nd. This is the depletion width on P side and depletion width on N side. Copy? Yeah. Next topic, calculation of total depletion width. Calculation of total depletion width. Yeah. See how to calculate the total depletion width in case of PN junction. See all of you. Now I am drawing PN junction in open circuited condition actually. Because of diffusion process, here depletion is misformed. So how to calculate this total depletion width actually in terms of barrier potential, right? See all of you. To calculate total depletion width actually here, consider electric field at any distance of x. What is electric field at any distance of x? Actually, dV by dx is equal to E into Na into x by epsilon plus E into Nd into Na into Wp by epsilon. This is the electric field at any distance of x in case of PN junction within a depletion region. Right? Consider this one as equation 1. Yeah. Now integrating on both sides. To calculate the total depletion width, actually integrate on both sides. So what is the integration actually here? V equal to, so integration of this function E into Na into x square by 2 epsilon plus E into Na into Wp by epsilon into x plus C2. Right. After integration, this is the function actually, right? Here to calculate this constant C2, use potential plot. Use potential versus distance plot. See this potential versus distance plot in case of PN junction. This is the potential versus distance plot. This is Wn, this is Vn, this is Wp minus Wp, this is Vp. Right. See here, to calculate C2, I am using potential versus distance plot. So in this plot, at x equal to 0, what will be the potential? See here, at x equal to 0. At x equal to 0, what will be the potential actually here? The potential is 0, right? If you substitute these conditions in this equation actually you will get the C2 value. Yeah, consider this one as equation 2 and consider this one as equation 3. Substitute equation 3 in equation 2. Then this is 0, this will be 0 and this also 0. Then what will be the C2 here? The C2 equal to 0, right? C2 equal to 0. Now this considers equation 4. Now substitute equation 4 in equation 2. Now what will be the potential? Actually V equal to E into Na into x square by 2 epsilon plus E into Na into Wp into x by epsilon. Right. Now consider this one as equation 5. Equation 5. Right. Now again substitute the conditions in this region actually. See here at x equal to 0. Actually what will be the built-in potential here? Built-in potential is nothing but difference of these two potential actually. See here built-in potential is nothing but difference of the two potential, right? Nothing but V naught equal to what here actually? Here the V naught is nothing but Vn minus Vp, right? Yeah, first you substitute these conditions actually. So at x is minus Wp, then what will be the potential actually? V equal to what? Vp. V equal to Vp, right? Then what is the Vp actually? See here. So at x equal to Wp, the potential is Vp. Vp equal to Vp minus Vp, right? Minus Vp equal to E into Na into, this is x square means Wp square by 2 epsilon plus E into Na into Wp, x is nothing but minus Wp by epsilon. Now which is equal to Vp equal to, right? So here simply it is minus E into Na into Wp square by 2 epsilon. This is the Vp value, right? Similarly, if you substitute at x equal to Wn, then what is the potential actually? Vn. Then what will be the Vn actually here? Vn is nothing but E into Nd into Wn square by 2 epsilon. Now what is the V naught here actually? V naught is nothing but Vn minus Vp. Now V naught equal to Vn. Vn is nothing but E into Nd into Wn square by 2 epsilon Vp. Here what is Vp? Minus of minus plus then E into Na into Wp square by 2 epsilon. Right. Yeah, copy up to this. So derivation is not completed. Copy. Right. Again consider this equation. V naught equal to what? V naught equal to common the E by 2 epsilon actually. Then Nd into Wn square plus Na into Wp square. Right. So it can be written as E by 2 epsilon into, see, write down like this, Nd into Wn into Wn plus Na into Wp square. See, what is the value of Nd into Wn actually? Na into Wp. Already we derived a relation actually. Relation between depletion width and concentration. What is the relation? Na into Wp equal to Wn into Nd, right? So this value is simply Na into Wp. Now V naught equal to E by 2 epsilon into, this is Na into Wp into Wn plus Na into Wp square. Here common the Na into Wp, then V naught equal to E by 2 epsilon, common this Na into Wp, then Wn plus Wp. Actually, what is the value of Wn plus Wp? Actually, Wn plus Wp is nothing but W. Now V naught equal to E into Na into Wp into W by 2 epsilon. Right. Actually, what is the value of depletion width on P side actually? This one also we derived, right? That is V naught equal to E NA by 2 epsilon into W. What is the value of WP actually? W into ND by NA plus ND, right? Now V naught equal to E by 2 epsilon into W square into NA into ND by NA plus ND. Now W square is equal to 2 into V naught epsilon by E into 1 by NA plus 1 by ND, right? Now what is the W actually? W is nothing but under root 2 into V naught epsilon by E into 1 by NA plus 1 by ND, right? So this is the expression of what actually? Calculation of the total depletion width in terms of the barrier potential and concentration, right? Very important equation. Yeah, copy. Yeah, completed. Next topic, calculation of magnetoelectric field in terms of total depletion width. Calculation of magnetoelectric field in terms of potential and total depletion width. This is also important expression actually. Yeah, copy now. Next, calculation of magnetoelectric field in terms of potential and total depletion width. Tell me what is the magnetoelectric field equation actually? Already we derived in any region actually. That is minus WP and 0 or 0 and WN. Now I am considering minus WP and 0 actually. That is E into NA into WP by epsilon. Right? This is the magnetoelectric field in the region minus WP and 0, right? Now see all of you, what is the WP depletion width on P side in terms of total depletion width actually? E into NA into, that is W into ND by NA plus ND, right? Now I can divide with, I can rearrange this equation like this, 2V naught by 2V naught. Epsilon also be there, right? Now I am rearranging this equation actually. Here. This is simply 2 into W by 2 into V naught epsilon V naught epsilon by E into 1 by NA plus 1 by Nd into 2V naught, right? What is this value actually? This value is nothing but simply it is a W square, right? Now what is the maximum electric field? Actually the maximum electric field is nothing but 2V naught by W. This is the maximum electric field in terms of barrier potential and total depletion width, right? Here from this equation actually I will tell one statement, actually one important point. See, for example, if the PN junction is a lightly doped PN junction, what I'm saying here, if the PN junction is lightly doped PN junction, right? What about the barrier potential? You know, the barrier potential is low, right? Barrier potential is equal to low. And what about the electric field? Actually, electric field is barrier potential is low, right? And depletion width. Depletion width is what actually? Depletion width is maximum or high. Depletion width is high. And what is the electric field? Actually, the electric field is maximum. Sorry, minimum, because W is high na, so electric field is minimum. Similarly, if the PN junction is heavily doped PN junction, if the PN junction is heavily doped PN junction, actually what will be the built-in potential? The built-in potential is high, okay, depletion width is low, and if depletion width is low means what will be the electric field? Actually the electric field is maximum, right? Yeah, copy. Right, write down, note, for a lightly doped PN junction, built-in potential is, for a lightly doped PN junction, built-in potential is low, depletion width is high, and electric field is minimum. Next point, for heavily doped PN junction, built-in potential is high, depletion width is low, and electric field is maximum. Right. Yeah, this is about electric field in terms of potential and depletion width. Write in a question, one example. Write in a question. In our classroom workbook, question number 1. In classroom workbook, question number 1. Write in a question. A silicon abrupt PN junction formed by is formed by adding 10 power 16 boron atoms per centimeter cube and 5 into 10 power 15 phosphorus atoms per centimeter cube. 5 into 10 power 15 phosphorus atoms per centimeter cube. If Ni equal to 1.5 into 10 power 10 per centimeter cube, 1.5 into 10 power 10 per centimeter cube, epsilon r equal to 11.2, calculate the first one, built-in potential, and second one, total depletion width, third one, maximum electric field, and fourth one, depletion width on P side and N side. Right. Yeah. All of you read the question once. What is the given data actually? They given a silicon PN junction is formed. By adding appropriate impurities That is boron. How much amount? 10 power 16 on n p side, and phosphorus 5 into 10 power 15. This is phosphorus, right? Uh, Boron means I think this is an acceptor, and the phosphorus means this is the donor. Also they given Ni equal to how much? 1.5 into 10 power 10, right, per centimeter cube. Next, also they given relative permittivity of silicon, that is epsilon r equal to 11.7. Here what we want to calculate actually the first bit, building potential. See, what is the formula for building potential actually? V naught equal to, in case of open circuited condition, V naught equal to Vt into ln of Na into Nd by Ni square. What is the Vt value at room temperature? 0.026 ln of Na, that is 10 power 16 into 5 into 10 power 15 by 1.5 into 10 power 10. So now what is the answer actually? 0.679 volts. This is the first bit. And the second bit. What is the second bit actually? Total depletion width. What is the formula for total depletion width actually? W equal to and root 2 V naught epsilon by E into 1 by Na plus 1 by Nd. 2 into V naught, that is 0.679 into epsilon. Actually, what is epsilon? Actually, epsilon is nothing but epsilon naught into epsilon r. What is the value of epsilon naught in CGS system? That is 8.85 into 10 to the power of minus 14. See, 12 is nothing but per meter, right? This is centimeter, na? So consider 10 power minus 14 into 11.7 by charge of electron, that is 1.6 into 10 power minus 19 into 1 by Na, that is 10 power 16 by plus 1 by 10 power 1 by 5 into 10 power 15. So this is equal to 0.517 micrometer. Right. This is the total depletion width. Second bit also completed, right? And the next one, third bit. What is the third bit actually? Maximum electric field, right? What is the maximum electric field in terms of potential and depletion width? Actually just now we derived, that is 2 V naught by W. Yeah, what is the V naught value obtained, right? 0.679. And what will be the total depletion width actually? 0.517 micrometer, that is 10 power minus 6. So this is equal to 26.2 kilovolt per centimeter, right? Next, fourth bit. What is the fourth bit? Depletion width on P side and N side, that is Wn and Wp, right? See all of you. What is the formula for Wp? Actually, Wp is nothing but W into Nd by Na plus Nd. What is the W actually? W is nothing but 0.57 into 10 to the power of minus 6. Nd is nothing but 5 into 10 power 15 by 10 power 16 plus 5 into 10 power 15. So which is equal to 0.172 micrometer, right? Wn. How to calculate the Wn actually? Here Wn is nothing but W minus Wp. Actually the total depletion width is nothing but Wn plus Wp, right? From this Wn is nothing but W minus Wp. W is nothing but 0.517 minus Wp is nothing but 0.172 micrometer. Then what is the answer actually? 0.345 micrometer. This is the Wn value, right? Copy. Right. Completed? Yeah. Thank you. To be continued in next lecture.